Lecture outline for this topic, and so this is what I'm using. And so if you review this so that you will be aware, you'll make sure you study those topics as we move through these subjects. Anyway, we are down here on calculations of equilibrium, and the next lecture, like I told you, is going to be a couple of lectures to get through all this, and I would like to do the equilibrium constant lab, which goes very quickly, a lot less complex than kinetics, and so the next lecture will be over these topics, so you'll at least know what to expect. So we want to teach you how to set these problems up and why I'm doing certain things as I'm doing. Okay. So problem 14, 29 from the worksheet. It reads, a 2.5 mole sample of phosphorus pentachloride dissociates at 160 degrees Celsius in 1 atmosphere to give 0.338 mole of phosphorus trichloride, PCl3, at equilibrium. What are the concentrations, what is the composition of the final reaction mixture? Now we're working in moles. You can't calculate a K value from this problem. Yeah, you can, because I'll make up a volume in that, but the problem as given, you cannot work the K value, but you can set up what we call the ice table. The ice table is set up like this. Let me make this larger. This is an ice table. Start out with the reaction written over here, and this, and whatever number of components, you have so many columns like this, and then you have a CI, change in C, equilibrium. That is initial concentrations, I, and then your change, C, and your equilibrium conditions, E, ice table. That's where it comes from. Now, you enter nothing's happened here. Only the concentration number, or the mole number, that is produced. Okay? Yeah. Is 0. So nothing's been produced. Then you allow it go through, this is really the kinetic region. This second row is moving through the kinetic region to the extent of reaction, or equilibrium region. So what happens, if you remember the graph that we've been drawing, the reactants go down, and of course you have the product concentrations going up. Now you don't know what they are, so you enter a variable, X or Y or whatever you want to use in there. So this one would go down by some molar amount in X, but the products over here would go up by whatever the coefficients are on those products, like that, and go up by X. And the algebraic sum of the initial and the change gives you the equilibrium concentration. So this would be 2.5, and of course it goes down in concentration, so you would expect to subtract an X, whatever is converted the product. And on this side, you see it's 1-to-1 over here, so it would go to X and X. Anybody understand what I just said? Kind of, sort of. Yes, ma'am. Okay, so in the problem it says phosphorus pentachloride dissociates at 160 in 1 atmosphere to give 0.338 mole at equilibrium. So this happens to be given 0.338 at equilibrium. And what I told you a moment ago is the sum of the initial and the change equals the equilibrium concentration. I'm going to recover this real quick. So with that, we can calculate what x is and get the rest of it. So from this, we get 0 plus x is equal to 0.338 mole. Therefore, x is equal to 0.338 mole. So that means I can come in here to under the chlorine, and enter 0.338 mole at equilibrium, and subtract the 0.338. Here it'd be, I'm running out of space here. Let me 2.5. Clean it up. 2.5 minus 0.338 mole. Right there. So the moles of PCl5 equals 2.5 minus 0.338 mole, which is, whatever that comes out to be, 2.162. Right there. So it's a logical progression leading to that last row from, if you can visualize the reaction and or the graph, this starts at, this is the reactants in the starting gate and they haven't generated anything, and then you allow the gates to open and it proceeds through the kinetic region and then forms the equilibrium concentrations or quantities as given in the table. All right, look at that next. Okay, nitrogen monoxide, NO, reacts with bromine to give nitrosyl bromide according to this reaction. All right, we'll start with the reaction. So I'll take 2NO gas plus bromine, Br2 gas, goes to nitrosyl bromide, to NOBr as a gas. And I'll draw my little table here. Initial, change, and then equilibrium. Come in here, 1, 2, 3, like this. C initial, change in C, and C at equilibrium. Isotope. Okay, so we read on. A sample of 0.052 mole of nitrous oxide reacts with 0.0262 mole of bromine. So we enter our data, 0.0524. Well, that looks horrible. O262. What's this one be? 0. That's exactly right. He hadn't started the reaction, so the first row is considered to still be in the starting gauge. So we need to go through changes. Now, what are the X things that we will put in here? Well, since this one is 2 moles, it will go 2X. Now it's going left to right, so this goes down by 2X, and you'll have the coefficient defining times whatever moles. This is 1, so it'll be a minus X. But what does this one do? It goes up, because you're producing that in terms of 2X. That makes sense, people? All right. Algebraic sum of these two would be 0.0524 minus 2X. This would be 0.0262 minus X. And 0 plus 2X are just simply 2X in there. Now, we read on. It says gives an equilibrium mixture containing 0.0311 mole of nitrosyl bromide. And it gives you a 0.0311. See, this is all of the nitrosyl bromide. However, that is equal to the 2X. Now think about that. Don't get confused on that. Okay, this is not X. It is everything given in the reaction chamber. But if you set up the algebra on this, it's a 2X there. And so 2X is equal to the 0.0311, sorry, which gives you X to equal 0.0311 over 2 mole. Whatever that comes out. Oh, 156 is X. So that'll allow us to now calculate the moles of each one of these in the reactant side. So moles of NO is equal to 0.0524 minus 2 times 0.0156 mole. And moles of the bromine is equal to 0.0212 minus 0.0156, which is just the X mole. And so we get the total moles. So you already given the moles up here and the product. And so yeah. Okay, thank you. Okay, so the nitrous oxide turns out to be 0.0212. That's where I got it on my notes. 0.0212 mole. And then this one would be 0.0106 mole. So everybody kind of see how I'm building the ice table to the equilibrium conditions based on data given? Okay. Now, if you need to calculate an equilibrium constant, the problem must give you a volume. And if the volume is given, you would take the moles divided by whatever the common volume is, because you have to visualize the amounts being in a fixed volume altogether. And so you would calculate the molar concentration by simply dividing by that whatever volume is given in the reaction chamber. So let's assume, for purposes of this problem, assume reaction chamber volume equals 6.0 liters. And these are the moles that you have. So in order to calculate the K value for this problem, one, you have to set up the equilibrium expression for the reaction. So you're given 2NO gas plus bromine gas in equilibrium with nitrosyl bromide, like that. And so the concentrations, the molar concentrations of each one would be the moles divided by, at equilibrium, let me put an EQ down there. At equilibrium would be the moles that we calculated in the ice table divided by the total volume. And so that would be for nitrous oxide, be 0.0156 divided by 6, 0.0516 mole divided by 6 liters. And so that one .0086 molar, and the bromine molarity would be 0.0106 divided by 6 liters. I got 0018 molar,
156, right?
and then we're given 0.0311, which is 0.0311 mole over 6 liters. And that's 0052. Wait a minute. Did I misfire? Correction, 035. And those are the ones you would apply to the equilibrium expression for the reaction. So now with that, we can write the Kc expression as concentration, molar concentration of NOBr squared and divided by nitrous oxide, also squared, and the Br2 to the first power. Everybody still with me? Okay. Then we simply substitute those values into the expression and solve for a number, which is a reflection of its extent of reaction. Now, of course, you'd be comparing it with some other reaction of similar nature and for whatever reasons you are doing the research. NOBr is 0.0052 molar. You can drop the units at this point and just put numbers in because it's the value that we're looking for. And so the NO squared would be a 0.0035 molar squared, and that's divided by 0018 to the first power. And y'all back me up on that. Okay. So the reaction would reflect a significant yield of product, and it would be way high relative to the concentration-wise of nitrosyl bromide versus the reactants of nitrous oxide and bromine. So it does essentially all you can tell from that issue. Now, what we're going to be ultimately getting into is, well, what if you start with certain concentrations and what will happen to the reaction? It will undergo a shift left or shift to the right. Now, in the one I'm just showing you, it shifts totally to the right because there's no product. It starts out with a load of reactants and goes to product. And there's a neat little relationships that I show the class, and we'll do this mostly in the next one, how to determine what the reaction will shift to, left or right, and how the new concentrations are generated for a new equilibrium. Let's take a look at some other outcomes. So 1434, you still build the equilibrium ice table just like you have in the past, but you're starting at the equilibrium end of the table and working backwards to the initial concentration according to question 1. Okay, so that's carbon monoxide plus hydrogen, molecular hydrogen, in equilibrium with methane, methyl alcohol, wood alcohol. And you've got Ci, change in C, and C at equilibrium. Now I'll get to the point where I'll just scribble it out. And put the numbers in. And you will too. You won't have to go through all the graphics and stuff. A 1.500 liter vessel was filled with 0.15 mole of carbon monoxide. Okay, 0.1500 mole of carbon monoxide and 0.3 mole of hydrogen. And when they came to equilibrium, the vessel contained carbon monoxide at 0.1187. How many moles of each substance were in the vessel at equilibrium is what we're asking. Well, of course, this is 0, and this is minus x, minus 2x, and this one goes to plus x. And so we can get our x out of this first column and fill in the other blanks. So 0.1500 minus x is equal to 0.1187, and this gives x to equal 0.1500 minus 0.1187. And what does that give us? Oh, 0313. So we can see it, and that's moles right here. So that is our x value. So this one would be 0.3 minus 2 times 0.0313. And this one would be x, 0.0313 mole times 2 equals negative plus 0.3, and I get 0.2374 here. And they give each one in terms of a 1.5 liter vessel. So these are the moles, but the molar concentrations at equilibrium for each one would be a result of dividing by 1.5. Volume equals 1.5 liters. So that would be 0.1187 over 1.5 molar for that one, and 0.2374 1.5 molar, and 0.0313 over 1.5 molar. If you are careful with entering your numbers into the equilibrium table, ice table, thinking about it as you go along, then you will be able to really check your work as you move through it, because it has to make sense as you approach the equilibrium. And in calculating the K, you should understand now that it's based on mole per liter, so that's what this row is involved. Now, some ice tables start out with molar concentrations, and all you have to do is just work down to the equilibrium in molar concentrations. The vessel's already taken into account. Maybe there's a problem in here we can look at as we go through that. So in this calculation, 0.1187 divided by 1.5, I get 0.0791 molar for the carbon monoxide. Try to keep it on the page. 0.23874 divided by 1.5 gives us a molar concentration of 0.1583. Keep me honest, guys. Back me up on this, please. 0.0313 divided by 1.5 gives us 0.0209 molar. Now those are the values you put into your equilibrium expression for the reaction now. So our Kc expression is methanol divided by carbon monoxide gas and H2 squared. So this is, of course, the CO. This is H2, and this one is OH, methanol, right here. So we have a 0.0209 divided by 0.0791 and 0.1583 squared. And I find the decimal, 77.7 is your K value. Well, it produces more products than reactants at equilibrium under the conditions given. Now you change the conditions, and we'll show you in the next class what happens to those reactions, because you'll shift to new equilibriums if you change three things: concentrations of the components, or you have an endothermic versus exothermic reaction, or it's pressure changes occur in the reaction, pressure volume changes. So that's called Le Chatelier's principle, and we will concentrate on that one extensively in the next lecture. Okay. Today. Okay, equilibrium constant and evaluations. So in problems 1435, it gives you some equations and simply asks you to write the equilibrium expressions. And only wrinkle that I gave you today is that if you are a heterogeneous reaction, you exclude solids and liquids. You include all gas phase components in the K value, Kc expression. I was looking down here to see if there is one. No, all of them are gas phase. So in the examples given in 1435, all of the components would be included in the equilibrium expressions. I'll just write out one here. That last one, D, if you're given PCl, is that 5? Yeah. And everybody's a gas. plus 3 ammonias, H3 as a gas, going to P phosphorus triamine is what that is, PNH2 3 as a gas, plus 3 HCl, hydrogen chloride as a gas. It's not an acid, it's not in water, so it's a byproduct gas form. So the Kc expression would be products over reactants again, PNH2 3 HCl gas cubed, and of course the problem would have to give you the molar concentrations to solve for a K expression. PCl5 gas raised to the first power, and ammonia gas, and that one's also cubed. So that all of them are written products over reactants, product of the concentrations of the product, molar concentrations of products divided by the product of the molar concentrations of reactants raised to the respective coefficient powers. Okay. Okay, given an equilibrium expression, how do you write the reaction from the K expression? So if you're given a Kc expression of CO cubed, CO2 cubed, and H2O to the fourth power divided by propane, C3H8 molar, and O2 to the, is that 5? I guess is that a 5 I got on the page?
Yeah, it's a 5.
Is it 5?
Mm-hmm.
Okay. My poor old eyes aren't supporting me. Okay, well, what are we looking at? Products over reactants, so you extract the reactants, C3H8, and there's only one of them. There's no power value. It's in gas phase. All of them are in gas phase, plus O2, and it's a power of 5, so it would be 5 coefficient, and that's in equilibrium with the CO2, and that'll have to be 3 moles of that in the gas and 4 moles of water and water vapor, like that. So it's just a matter of reversing the K expression notations into an equation, and remembering the top is the products and the bottom is the reactants. Say if you're given Kc for forward reaction, K for reverse, KEQ for reverse reaction is equal to 1 over K for the forward reaction. That's the essence of that rule. Anyway, in the problem that's given, they gave you an I2 gas plus H2 gas in equilibrium with 2HI as a gas. So Kc forward is equal to HI squared. That should be brackets, I'm sorry. HI gas squared over I2 gas and H2 gas, like that. So Kc reverse equals 1 over Kc forward is then just the reciprocal of that, so you turn it upside down, and you would have I2 gas, H2 gas, and HI squared. Everybody good on that? So it's just flipping it over. Now, problems will come to you like this, though. Let's assume, assume given Kc forward is equal to, say, 2.35, just a given number. What is the reverse Kc reverse? Well, of course, it's just 1 over that number. So Kc reverse being 1 over Kc forward would be 1 over 2.35. Just putting it in your notes so that you will be aware of it. That's a 5, believe it or not. I'm going to get 2.35 and take the reciprocal, 0.426. And so that would be your K value for the reverse reaction. So it's not too efficient going in that direction. That's all it means. Everybody good on that? Just hitting some high points right now. Okay, I'm sorry. Okay, 1439 on the worksheet. I'm giving you the equation off of the problem here. And then it wants to know what the Kc for 1/2 of the reverse reaction is. So I'm going to cut the reverse the reaction, 2.25, and goes to 4NO gas plus O2 gas, like that. So that would give us N2O5 gas equilibrium with 2NO gas plus 1/2 O2 gas, like that. Start with the equilibrium expression of the first reaction. Say Kc for number 1 is, let's just go N2O5 squared divided by NO2 to the 4th power and O2 to the 1st power, like that. Then over here you put Kc2, the second reaction, or prime, or however you want to look at, and products over reactants, NO squared, O2 to the 1/2 this time, divided by NO squared. Even if I'd have written it according to the listed problem, you still do the same thing. Now the question is, how do you go from the first one to the second one? Look at this, and then look at this. What did you do here between this one and this one? If you take this one and flip it over, all you did was take the reciprocal of the square root, if you look at it. Yes? Yes. You see how that, everybody see how that's a reciprocal of the square root? So you have to look at each one and say, how did I go from the given to the question, which is cut it in half and reverse, like that. So Kc2 is simply equal to 1 over the square root of Kc1. Now, if given the value for Kc1, let's say let Kc1 equal 1.12, something like that, what is the Kc for the reverse reaction? Then that would be 1 over the square root of 1.12. And that would give you whatever the, make it 2, because that would be a little more realistic. Make that a 2. 2.12, I take the square root and the reciprocal, and I have 0.687. If you took the 2.12 and took the double that and took the reciprocal, you would not get this. You have to do this so that you will see the square root function in that mental process, going from here to here. But if you just take that and double it and take the reciprocal, that's wrong approach. That's why I say it's a mental thing at this point. So that's why I say even if I wrote it as given, I would still go through the first equilibrium expression, second equilibrium expression, which is the question, and look how to, and ask myself how to get to the, from one to the other. Everybody kind of see the mental thing here? Everybody good? Any questions? Okay, some of them get kind of pinky if you don't do that. You won't see it. And don't make assumptions that are incorrect relative to changing from one equilibrium constant to the next. And hopefully I can write the rest of it. Equilibrium constant Kc for the equation, yada yada yada, 27. So this is a case where what's the equilibrium for the equation next one? So it's done just like I did this one. Let's see. Let's look at that one. Okay, so 1442, and let's see if I can write it correctly this time. Okay, so you're given an equation CS2, and it's all gas, so save space, 4 hydrogens, and CH4, and 2H2S as a gas. Okay, and the Kc for this reaction is 27.8. What is the Kc for this? So we have half of CH4 and H2S and equilibrium with half of CS2 and 2H2, all gas phase. Okay. So you write the equilibrium expression of the first one, write the equilibrium expression of the second one, ask yourself how did you go from 1 to 2, set up your equation between K1 and K2, and then substitute your value for K1, and you get your answer. So K1 is equal to CH4 H2 squared over CS2 and H2 to the 4th power, and then K2 is equal to CS2 to the 1/2 H2 to the 2nd power, and then we have CH4 to the 1/2 and H2S to the 1st power, like this. So how do we go from 1 to 2? So when I compare the two, it looks like just what we talked about. It's the reciprocal of the square root, right? Wouldn't you think? So I can say K2 now is 1 over the square root of K1. Substitute your value, 27.8, and voila, answer, and you pick that choice. .19. And so, let's see what else we've got in here. Trying to get it on. Okay, so in this kind of problem, when it comes to you as you read it, it'll tell you well, it's got all this numbers and stuff, is already at equilibrium. And so you apply it to just the equilibrium row in the ice table. So let's see what this says. A 6-liter reaction vessel contains 0.488 mole of hydrogen, 0.206 mole of iodine, and 2.25 mole of hydrogen iodide. Assuming the substances are at equilibrium, find the K for the given reaction. So you're given the I2 gas plus H2 gas in equilibrium with 2HI gas, but all you need is the equilibrium row here and the quantities in moles, and then convert them to moles per liter and solve for your K value. So you're given hydrogen, if I can write hydrogen looking like hydrogen, there you go, 0.488 mole and 0.206 mole, and hydrogen iodide 2.25 mole. Now, to solve this problem, we have to divide by 6 liters. And then substitute it into the Kc expression, which is Hi squared over I2 squared and H2 to the first power, like that. So I get these values, and so you see how I'm just working with the equilibrium row because that's what the problem specifies. And so I substitute 0.375 and 0.3034. And that's squared, and 0.081.
Why is I2 squared?
That's better. And times 0.081 is equal to the reciprocal times 0.375. Okay, so we get 51. Okay, so just that's the point of this problem, is that be careful of how you read it. You may not have to deal with all of the ice table. You're given Kc for the reaction is 0.28 for reaction. Just then, what's Kp for this reaction? Well, I got to have it. Let me put the reaction down. I got the CS2 gas plus 4H2 is a gas, almost through, CH4 gas plus 2H2S as a gas. So when we look at this 4 or 5 molar volumes and 2, 3 molar volumes, so the change in molar volumes is N, so that's 3 minus 5 VMs, which is a minus 2 VMs, and this gives N to equal minus 2 in the Kc equals Kp expression. So Kp equals Kc RT to the delta N. So the Kc was given to be 0.28, 0.28, R 0.08206. And the temperature, we'll give a temperature, 900 degrees Celsius. So that's 900 plus 273, 379, 10, 11 Kelvin. So we need to put 1173 Kelvin And so you don't even have to put the units in here to raise to the -2 power and solve that. And you get a number. And that's the KP expression, KP value for that reaction, okay, based on the KC expression. So that only thing you have to really worry about is, well, that's a constant, that's a given, and then that's a temperature in Kelvin, and then put in -2 and compute